Hello, this is the lesson 2 of Calculus for engineering students, and today we are going to focus on the limits of sequences. So sequences is basically a function defined on positive integers, that is its definition. And the limit of sequences is defined as the below statement, this thing. So we assume that Fn is a sequence, and it is the sequence of Fn is defined as this statement. So it means that for all epsilon greater than 0, there exists a big N that is a positive integer, such that the statement n is greater than big N implies Fn minus a, the absolute value of Fn minus a is smaller than epsilon. It's smaller than epsilon. So this is its definition, and there are some properties of the limit of sequences. So if the limit of a sequence exists, then it must have only one value. So for this, we can use the proof by contradiction method to prove it. So we say that this thing can equal to A and B. So according to the definition, we would have and for the circumstance when the Fn equals to B, this is also the same, except we will have to change this to the N1 to N2, and here the A to B. So this is a necessary and sufficient condition derived from the statement. So we assume that it has two values, and here the A is not equal to B, and we try to find some paradoxes. So here, because the epsilon is greater than 0 and it has two values, B and A, without loss of generosity, we assume that the B is greater than the A. So we take epsilon equals to the average of B and minus A. So we take that value, and you can see that a paradox can be derived. So using this statement, we have the following condition. And also, and by expanding these two terms, we find a paradox, which is this. So there exists a big N, which is equals to the max of N1 and N2, such that when the small n is greater than the big N, Fn is greater than the average of A and B, and also Fn is smaller than the average of A and B. So this is apparently a paradox, so it is proven, so this property is proven. And the second property. So the second property states that if the this one exists, then it must have a boundary. So how to prove this? So we can write the necessary and sufficient condition for this statement. That is this one. We have this one. So here we consider the value of the following thing, which is the value of this. So this is apparently equals to this thing. So this one is equals to this one is so this absolute value is smaller or equal to this one. So as we know before, this statement is true. So we can take the epsilon here to be, let us say, the absolute value of A. So this thing here must be smaller to the A plus the epsilon, which is the 2, the absolute, twice of the absolute value of A. So we have, because of these relationships, we have this statement. We have this statement. So this is apparently the form of this, which is by definition, this should be M. By definition, the boundary of the Fn should be the M. But be attention here. So here we the premise of this statement is that the n is greater than the big N. So we would have to consider the circumstance when the n is smaller or equal to the big N. So for these circumstances, we take, let us say, a z, which is equals to the maximum value of 2a, absolute value, and f1 all the way to fn, big N. So apparently we would have fn, absolute value, is smaller than the z. So this statement is proven. So this is how we prove the second property. And the third property. So the third property states that if the this thing exists and the value of it, which is a, is greater than 0 or smaller than 0, but the proof is quite similar. So we will only consider the circumstance when it is greater than 0. Then there exists a positive integer, such that when the n is greater than that positive integer, the fn is greater than 0. So what do we do here? So according to the definition, so this is what we get from the definition. And here, let me expand this. So that will result in so We know that we have a epsilon that is greater than 0. Whenever we take an epsilon that is greater than 0, the following statement from here to here all stands. So let us just take the epsilon that is, because we want to prove this thing, so we take the epsilon that is equal to the a. And because a is greater than 0, so this value for epsilon is suitable. And we have this. So it is proven. The Fn is greater than 0. We just take this. So this third property is proven. And the fourth property. We do not have the fourth property, but let me foretell. So the fourth property is told in the lessons that will precede this one. So the fourth property is basically this. So we have three series, and let's just name them F1n and F2n and F3n. So if this relationship stands, and the limit of this is a, and the limit of this is a, then the limit of F2n must be a. And this is what the fourth property says, but we will talk about that later. So here are some exercises. So the first one asks us to compute this one. So let us first look at the definition for limit of sequences. So this basically tells the idea of infinitely approaching. Like we can draw a graph, which is like this, but be aware. So this thing is defined on the set of positive integers. So be careful. It is not a consistent graph. So this is a little graph. And for this thing, we would imagine that it is like this. Let me wait. Basically like this. So what this definition tells you is that as the input value, the n, here the n, and this is the Fn, approaches infinity, which is way beyond there, what does this value approaches? So from the graph, you can observe that it is apparently 0. So this is 0. We can prove it, but the question doesn't ask us to prove it, so it doesn't matter. And the second question asks us to prove this statement. So how can we prove this statement? So we would imagine that we would have to make this Fn. Here the Fn is equals to this one. Make the Fn minus 0, the absolute value of it, smaller than epsilon. Smaller than epsilon. And here the n is greater than 0, because the n is greater than a positive integer n, a big N. So the n must be greater than 0. And here we have this one. And because the n is greater than 0, this stands. So we would naturally imagine that we can take the epsilon by solving this equation. So we have this. And we have this. So we can take the n, which is equals to this thing, and we find this n, and such that for any epsilon greater than 0, there exists a n which is equals to the square root of the reciprocal of the epsilon, and such that for any n that is greater than the big N, we have this Fn minus 0, absolute value smaller than the epsilon. So this thing is proven. Oh, and this is the fourth property. And the fourth property we will prove it now. So the fourth property, what do we do? So for the fourth property, it says that we have three sequences, and if it meets the following conditions, these three conditions, then the limit of Gn must be A. So what we do is here, according to the definition. So we expand this this expression, and here we have the Fn is smaller than A plus epsilon and greater than A minus epsilon. We have this, and similarly we do this to the Hn. And we find that the Hn is smaller than the A plus epsilon and greater than the A minus epsilon. But here, these two statements are only true when the like this statement is true when the n is greater than the n1, and this is only true when n is greater than the n2. And what we are going to prove is this one. So this one, it demands that the n must be greater than a given positive integer. So we take n as the maximum of n1 and n2. So we have when the n is greater than the big N, these two statements, because this is the maximum of these two, both stands. So we have this one, and because this condition, so this also stands. So we have this one when n is greater than the big N. So we have this statement. And what this means is this one. If we write it in we're with an absolute value. So combining with this premise, we have for any epsilon greater than 0, there exists a big N that is a positive integer, such that we can start from this, and it implies that this one, here we use Gn, minus A is smaller than epsilon. So this is proven according to the definition.